Starship's deep space promise a cosmic feat or a fatal flaw. The Starship system, with its unprecedented promise of full reusability and immense payload capacity, stands poised to redefine humanity's reach into the cosmos, fundamentally altering how we conceive and execute deep space missions from a communication and scientific return perspective. However, as detailed in ongoing assessments by space systems engineers and operational analysts, the inherent complexities of its proposed heat shield reuse and intricate orbital refueling sequences for interplanetary trajectories raise critical questions about its ultimate reliability and mission assurance for our most invaluable scientific endeavors. This examination will delve into whether this ambitious design truly paves a reliable path to deep space, or introduces an array of challenges demanding an unprecedented level of operational maturity. From the profound vantage point of those who routinely bridge the vast, silent chasms between worlds, the Starship concept emerges as a potentially epoch-making advancement, promising to fundamentally redefine the very parameters of deep space exploration. Its ambitious blueprint, centered on unprecedented full reusability and an astounding payload capacity, offers a tangible path to transcend the inherent mass and volume limitations that have historically governed our probes and telescopes. This paradigm shift could enable the deployment of scientific instruments of unprecedented scale and sophistication, allowing for higher resolution imaging, more sensitive spectral analysis, and the integration of diverse sensor suites that are currently unfeasible due to launch constraints. Moreover, the ability to lift more robust propulsion systems directly into orbit promises to shorten transit times to distant targets, thereby enhancing mission responsiveness and improving data return windows, a critical factor for communication link budgets. Beyond robotics, Starship could facilitate a truly sustained human presence beyond Earth orbit, enabling the direct launch of complex habitats, life support systems, and even manufacturing capabilities that foster self-sufficiency. This capacity ignites what some within the scientific community have termed an impossible question: what truly ambitious missions, previously confined to theoretical studies or speculative fiction, might now shift from the realm of the impossible into the domain of engineering challenges. Consider, for instance, the potential for vastly larger space telescopes, perhaps eclipsing the aperture of the James Webb Space Telescope, to be fully assembled on the ground and delivered directly to their operational orbits, dramatically enhancing our observational power for exoplanet characterization or the study of the early universe. For planetary science, Starship could transport multi-ton rovers equipped with advanced drilling and sampling apparatus to icy moons like Europa or Enceladus, capable of sophisticated in situ analysis that far surpasses the capabilities of current mass-constrained designs. The ability to launch an entire integrated Mars sample return mission architecture, from ascent vehicle to Earth entry capsule, could streamline operations and reduce points of failure compared to multi-launch, multi-rendezvous approaches. Furthermore, from a deep space communication perspective, Starship's immense lift capability could revolutionize our global deep space network. It might enable the launch of significantly larger, more powerful, and fully redundant communication relays to strategic locations within the solar system, ensuring continuous, high-bandwidth links with our most distant explorers, mitigating the current reliance on intermittent ground station passes, as often discussed in DSN architecture studies. This could even extend to deploying space-based DSN assets, a concept periodically explored to enhance coverage and overcome terrestrial limitations. However, this inspiring vision, one that promises to unlock new frontiers of discovery, is inescapably tethered to a unique set of engineering and operational challenges that demand rigorous scrutiny. The very concept of reliably committing invaluable deep space assets often representing decades of scientific endeavor and billions in investment. To a system of this scale and innovative design necessitates an unparalleled level of demonstrated performance. The ambitious reusability goal, while economically appealing, introduces complex thermomechanical and structural integrity considerations for components like the heat shield that must withstand multiple extreme atmospheric re-entries. Our historical experience, from early space shuttle development to recent atmospheric flight test observations, consistently underscores the inherent difficulties in achieving routine, high-reliability reusability at such scales. Thus, the transformative potential of Starship is matched by the profound imperative for meticulous validation and a conservative approach to mission assurance, particularly when considering the unforgiving nature of interplanetary travel, where a single anomaly can jeopardize an entire scientific legacy. Our collective journey into the deep reaches of space, often spanning millions or even billions of miles, has indelibly taught us that the success of any mission hinges upon the impeccable performance of every single component. Unlike terrestrial or even low Earth orbit operations, there is no quick return, no easy repair, and certainly no second chance for a system traveling years from home. The unforgiving vacuum, extreme temperatures, and pervasive radiation environment of interplanetary space amplify even the slightest anomaly into a potentially mission-ending event, a reality acutely felt by those responsible for maintaining distant communication links. Against this backdrop, the foundational challenges inherent in the Starship architecture, particularly its reliance on routine reusability and complex orbital assembly for deep space injection, demand rigorous scrutiny. The concept of routinely reusing an advanced heat shield, for example, forms a cornerstone of Starship's proposed economic model, yet it introduces profound material science and aerodynamic complexities. Each atmospheric re-entry subjects the vehicle's thermal protection system to immense thermal and mechanical stresses, demanding materials that can repeatedly withstand superheated plasma, extreme pressure loads, and rapid temperature cycling. The integrity shield is not merely an operational concern. It directly impacts the safety and stability of any sensitive deep space payload nestled within. Ensuring that such a system maintains an unprecedented level of reliability flight after flight for instruments designed to scrutinize distant galaxies or sample alien oceans requires a robust inspection, refurbishment, and requalification process that pushes the boundaries of current aerospace practices, as often discussed in conferences on space system longevity. Damage or degradation that might be deemed acceptable for a commercial LEO payload could represent an unacceptable risk for a multi-billion-dollar interplanetary mission where data continuity over years or decades is paramount. Further compounding these challenges is the necessity for extensive orbital refueling, a technically elegant but operationally daunting ballet of multiple cryogenic propellant transfers performed in the vacuum of space. Unlike the relatively simple transfer of non-cryogenic consumables to the International Space Station, Starship requires the precise, large-scale movement of super-cold liquid oxygen and methane between vehicles, a process fraught with engineering hurdles. Cryogenic fluids are prone to boil off, slosh dynamics, and thermal stratification in microgravity, making efficient and complete transfer difficult. Each instance of docking, each connection of fluid lines, and each transfer operation introduces a discrete probability of failure. When these events are chained together multiple times, as envisioned for a fully fueled Starship departing for the Moon or Mars, the cumulative probability of an anomaly can escalate by orders of magnitude beyond what is typically acceptable for a single-use upper stage, a concern frequently voiced in discussions around risk assessment for complex space operations. Such a protracted and intricate sequence of maneuvers would also place significant demands on telemetry and command capabilities from Earth, potentially straining the resources of global networks, like the Deep Space Network during critical phases. Finally, the sheer launch cadence required to support this ambitious refueling architecture presents immense logistical and operational demands on both ground and space infrastructure. To fully fuel a Starship for deep space, numerous tanker starships must ascend to orbit, rendezvous, and offload their propellant within a relatively short window to minimize boil-off and meet planetary departure opportunities. This necessitates an unrelenting tempo of manufacturing, ground processing, launch operations, and regulatory approvals. The resilience of launch facilities, the availability of launch ranges, and the coordination of vast teams of engineers and technicians must be unwavering. Missing a planetary departure window due to a delay in cadence, perhaps from weather or a technical issue, could mean a multi-year postponement for missions, targeting specific celestial alignments, impacting scientific timelines, budget cycles, and the long-term viability of entire research programs. The intricate dance of bringing together hardware, propellant, and precise timing in a serial, high-frequency operation is a test of industrial capacity and operational discipline unprecedented in the history of large-scale spaceflight. The successful, repeated execution of these demanding, interconnected operations underpins the very feasibility of Starship's deep space aspirations for institutions dedicated to traversing the vastness of the cosmos and ensuring the continuous, vital flow of data from humanity's distant robotic envoys. Mission assurance stands as the paramount imperative. It is the unyielding foundation upon which all deep space endeavors are constructed, a principle deeply ingrained within operations that routinely manage spacecraft millions or billions of miles from Earth. The critical trade-off between minimizing launch costs and maximizing reliability becomes starkly apparent when contemplating the monumental investment in a multi-billion-dollar scientific instrument or the sheer audacity of a decade-long interplanetary journey. While rapid iteration and cost reduction are certainly valuable drivers in the broader space economy, the unforgiving nature of the deep space environment magnifies even what might be considered minor failures in other contexts, transforming them into catastrophic losses. This reality demands a distinct philosophy of risk tolerance for missions whose success or failure determines the advancement of human knowledge for generations. Consider the immense stakes involved in flagship missions, such as the Europa Clipper, designed to investigate the habitability of Jupiter's icy moon, or the James Webb Space Telescope, JWST, peering back to the very dawn of the universe. Each of these represents not merely a piece of hardware, but decades of scientific inquiry, engineering brilliance, and international collaboration. A launch vehicle tasked with delivering such irreplaceable assets to their precise interplanetary trajectories or orbital vantage points must demonstrate an exceptionally high probability of success. A single anomaly during the ascent phase, the translunar injection, or the deep space departure burn can negate years of painstaking development, extinguish scientific opportunity for an entire generation, and result in the irrecoverable loss of financial resources. Unlike commercial satellite deployments, where individual failures, while costly, do not necessarily undermine an entire programmatic strategy, the loss of a unique deep space explorer leaves an irreplaceable void. The challenges inherent in operating within the deep space communication infrastructure further underscore this need for unwavering reliability. Our deep space network facilities, positioned strategically around the globe, are built to listen for the faint whispers of spacecraft at the very edge of our solar system, interpreting complex telemetry and receiving scientific observations. However, this entire system, from ground to space, depends utterly on the successful deployment of the mission vehicle itself. If the primary transport system falters, there is no mission, and consequently, no data to acquire, process, or disseminate. The continuous flow of critical data back to Earth, which drives scientific discovery and informs future endeavors, is entirely contingent upon the launch vehicle's flawless execution. Historical precedents, from the Mariner series to the Voyagers, demonstrate that long-duration missions demand not just initial success, but a robust design capable of enduring the perils of space for decades, a robustness that must begin with the delivery system. Therefore, any launch system proposed for deep space transport, despite its innovative potential or ambitious design, must mature to an unparalleled level of operational robustness and predictability. This maturity is not merely about achieving a few successful test flights. It encompasses a comprehensive demonstration of reliability across all mission-critical phases, a rigorous understanding of failure modes, and a proven ability to consistently perform within demanding operational envelopes. It must instill unwavering confidence in its capacity to deliver invaluable payloads safely and precisely, ensuring that the billions invested in scientific instruments and the years of human ingenuity behind them are not squandered. The true measure of a deep space launch vehicle lies in its proven ability to consistently safeguard these extraordinary ventures, guaranteeing the continuous stream of discovery that flows back to humanity. The Starship system indeed offers an unprecedented vision for deep space exploration, yet realizing this ambition hinges entirely on overcoming its profound engineering and operational complexities, particularly regarding routine reusability and intricate orbital refueling. Our collective experience in safeguarding invaluable interplanetary missions dictates that cost efficiency cannot compromise the unwavering reliability critical for multi-billion-dollar scientific endeavors. Ultimately, the question remains whether Starship will deliver on its promise as a cosmic feat, or if its inherent complexities will prove to be a fatal flaw for humanity's most ambitious journeys beyond Earth's embrace. True mission success will be measured in the consistent, safe delivery of our precious scientific instruments, ensuring the continuous flow of discovery. If this in-depth analysis of Starship's intricate challenges and monumental potential for deep space missions resonated with your understanding of space exploration, please consider supporting Tech Dissect Official by liking this video and subscribing for more rigorous examinations of aerospace innovation. What specific Starship operational challenge, from heat shield reuse to the extensive orbital refueling sequences, do you believe poses the greatest hurdle for future deep space missions? Thank you for joining us on this critical discussion as we navigate the complexities of humanity's next giant leaps. We eagerly anticipate exploring more frontiers with you soon. Next time, we'll delve into the fascinating world of quantum communication and its potential to revolutionize how we connect with our most distant spacecraft.